Welcome to the Abstract Synthesis Podcast, where we share the stories behind fascinating academic papers in the world of program synthesis and neurosymbolic AI. This podcast is brought to you by AGI Research Lab and DIA, and I'll be your host, Brian Landers. All right, folks, couldn't be more excited for today's guests. We're going to anchor this episode on a paper called Why Creativity Cannot Be Interpolated, which was published earlier this year in February in 2026. One of the authors is a friend of NDIA and ArcPrize teams who I've had the pleasure to get to know over all these years. Just 3 now, I guess, that we've started ArcPrize, or 2 maybe. So much has happened in this world. But he hosts one of the most influential AI podcasts called Machine Learning Street Talk, or MLST, and they produce long-form conversations with top researchers, and they do it with just the highest quality bar of any podcast I've seen. So I'm honored to have them on. And his co-author, his research bridges mathematics, machine learning, foundations of artificial intelligence. Quick shout out to a listener of the pod, Enrique Shea, who suggested today's paper. And I immediately sent it over to the authors and said, would you guys be down to do this? And they kindly agreed to jump on. So without further ado, let me pass the mic to our guests. Can you please introduce yourselves?
Cheers, Brian. Well, yeah, so I'm Tim Scarfe. I run MLST, and it's now my full-time job as of about 2 years ago. So I get to live the dream. I travel around the world, and I've interviewed some very, very fascinating scientists and philosophers and AI researchers. And honestly, it's a great. I'm a very lucky guy.
Hi, I'm Jeremy Budd. So I'm an assistant professor at the University of Birmingham in mathematics, and I got into all of this space with doing mathematical methods for understanding images, because it's such a different way of applying the maths I'd learned about in uni. And then when machine learning colonized the entirety of the image processing domain, that got me into learning about machine learning. And now I'm here.
Super cool. All right. I want to learn a little bit more about your backgrounds, just because, before we dive into the paper, we want to know, who are we talking to? Who are these authors and why did they come to this really cool thesis? So Tim, let's start with you. Your background leans very technical. You've been principal engineer at Microsoft, chief data scientist at BP. You've got degrees in machine learning, computer science. How on earth did you end up being this kind of, philosopher / media mogul?
Well, first of all, I'm definitely not a philosopher. Jeremy is far more of a philosopher than I am. Although even Jeremy, you would say it's mostly, the result of having a lot of arguments on Reddit when he was younger. But part of it is MLST is an interesting podcast because we kind of communicate ideas in a multidisciplinary way, which means we go quite high up the abstraction mountain. And it's always a trade-off because a lot of people say to us, oh, well, this is just kind of academic jargon. I don't understand what you're talking about. But, the good thing about MLST is through this multidisciplinary language, we make our ideas more legible to folks working in, cognitive philosophy, psychology, physics, computer science, mathematics, and so on. So you see there's a little bit of a balance there. But I've always been really interested in certain ideas in philosophy. So, for example, the philosophy of intelligence, which was very much inspired by our mutual friend François Chollet, the philosophy of agency, the philosophy of creativity, the philosophy of knowledge. Jeremy is very interested in the philosophy of value as well, so value-type questions. And, a lot of this actually kind of It came from many of the interviews I did on MLST. We started as a technical ML research podcast, and then we spoke to folks like, François Chollet, Kevin Stanley, Carl Friston, Noam Chomsky, so many. I mean, even recently this year, Marvitsa Chiramuta and Cesar Hidalgo. And it just opened up a whole new world for me. And this is what I'm saying. I'm in such a privileged position because before working in my corporate job, I was very focused on just doing engineering and software and just making systems work. And now I have the opportunity to speak with these amazing people, and they've planted the seed in me. We've got a Discord community as well. So it's not just me. We talk on the Discord community, and it's just created this whole thing.
I've just heard such great things. A lot of the folks that are involved with ArcPrize and NDIA are fans of the show, have discovered, teammates of ours or even François on your podcast. I can't tell you how many times I've heard, oh yeah, I saw, François on the MLST podcast. That was a great episode. So it's been just a huge impact on the community at large. I'm really glad you took the leap into that adventure, and you're just really excellent at it too. Like I said, the quality bar is through the roof. So keep it going. I can't wait to see what other fun documentaries you get up to. And Jeremy, how about you? Yeah, man, your background, Jeremy, is, I believe, you mentioned like mathematics, and you've done very cool work, I think personally, on graph-based learning methods for image processing, which you were alluding to earlier. What led you to that focus? I kind of like, in my brain, the story I tell is you were like a math genius kid, and that's how you kind of got into it. But you tell me the reality.
I mean, I was good at maths at school. I mean, the story really goes back to my grandfather. He was very good at maths, but was encouraged in different directions, ended up becoming a vicar. And so after he retired, he went back and did like an Open University maths course. But when I was growing up, he was really influential on me of teaching me all about all these cool things in maths. So I always knew quite a lot more. But my dad's also a mathematician. It's a whole thing in the family. So then when I got to university, I thought at first I was going to be really interested in like pure mathematics of set theory and number theory and these sorts of things. But I always found myself being drawn towards applied mathematics stuff because there were certain ideas that would sort of emerge out of real world questions that would involve mathematics that already existed, but also would involve new mathematics. And it was just sort of, I found that really exciting, that dynamic. And so one time when I was an undergrad, I was a student helper at a conference that was being hosted at the maths department. And so our job was just like to sit in the back and make sure that if the projectors turned off, we could turn them back on. Yeah. But we got to watch all of these great talks as undergrads. And so one of these talks was about using these differential equation flows on finite discrete graphs to analyze images. And I just found this was like such a cool idea, combining these things I'd never thought about before and putting all of this stuff in this completely different context. And so I found that a really cool talk. And then by complete luck, when I was applying for PhDs, that same guy was advertising a PhD project in exactly that area. And so I sent him an email, and actually I'd forgotten that he'd given that talk. So I just went, oh, this is like that really cool talk I went to a few years ago. And he was like, oh, I'm glad you like my talk. And so then that sort of got me into doing this graph-based stuff. So I just really loved how it was taking all of these ideas from continuous analysis and phase separations and all this various stuff, and transporting it into this completely different domain so that you could analyze images. And I really enjoyed the methods that we worked on, and my supervisor and I have written a book about it. So that's that was really great. The trouble is it's harder to get people excited about those ideas these days when it's like, or we could just hit it with a transformer, and so we're still figuring out how to combine the best of both worlds to get people still excited about graph-based methods. But I mean, yeah, graphs are just a lovely way of representing and thinking about data, and definitely still very important in the AI world. And yeah.
Oh, I couldn't agree more. And that sort of, that sort of combination is the thesis of our research at India, and pretty much the topic of this podcast. I had Loris D'Antoni, UCSD program synthesis professor, on last episode, talking about this exact dynamic of like, he's been working in symbolic AI for decades, and here comes transformers and the LLM era, and it's like, is my job like gone now, like because of one, API call to, GPT-5, whatever? But the answer was no. There's plenty of, opportunity to kind of, go across these sort of fields to add value. So I'm a huge proponent of that. So I think you're pulling on the right threads. Well, I guess, let's jump into the paper if we can. So we're here to talk about why creativity cannot be interpolated. I found this paper really interesting. It sort of read, it's beautiful writing. There's some like really poetic writing even at the end that I was like, wow, like I can't believe I'm reading an academic paper that's like so beautifully written. But it does feel kind of like you had sort of culminated like all these ideas, about intelligence and the definition of intelligence. What was the story behind this paper? Like, you cited the sort of thinkers that came before that you built a lot of your ideas on so well in the paper. So we can see kind of where you were sort of digging for ideas. But what sort of sparked, like, Jeremy, Tim talking, like, we need to do this paper right now. Like, this is the moment with all this stuff changing, and we're gonna launch these ideas and plant a stake in the ground about what we believe about intelligence.
So the spark really was, there was an MIT CBMM panel back in 2023 that had Demis Hassabis and Sutskever and I think Hinton, I can't remember who was there. Pietro Perona, who is a really great imaging person at Caltech. So that was fun. In that, Demis Hassabis sort of talked about his vision of like what AI creativity could look like. He talked about it before, but it was when we first came across it, of where he talks about like the lowest level being sort of interpolative creativity, sort of combining things that already exist into new things. And then his sort of extrapolative creativity of sort of going beyond the things that already exist. And then finally, he gave like AlphaGo's Move 37 as the example for that. And then like the highest level being like inventive creativity. So anyway, that set off like a really big conversation in the Discord, the MLST Discord about stuff, and I wrote like this really, really long Discord comment on reacting to that, and Tim was just like, "Oh, we should make something longer." With
a long time ago.
Yeah, so that was 3 years ago.
Wow.
And then the paper the article went through like various levels of complete rewrite. So like when it started off, we were thinking in a very sort of Fristonian way of like active inference and free energy and that sort of thing. And then we actually read a whole bunch of literature on creativity that helped. So like we started off with, just the very short introduction to creativity as where, always a good place to start those books. And then, just digging through loads and loads of papers. And then sort of had a bit of a reframing. Maybe we'll talk about like creative reasoning. And then the thing that turned it into the version that you now see was the Kenneth Stanley fractured entangled representations work, and thinking about Picbreeder, and that gave us a bit more of like an organizing principle, and this idea of sort of the phylogeny and all of this. And
Yeah, I think, as you probably saw, we were trying to weave together what François Chollet says and what Kenneth Stanley says, because, we are collectors of ideas on MLST, and we are trying to make sense of it in context, because it seems like what Chollet is talking about is creativity, right? So, intelligence is the adaptive synthesis, crystallization of skill. And that can be a creative process on its face, right? So, here's a problem statement, and I have some core knowledge, and just like Lego, I'm stacking them together, and I'm solving this problem, and I'm creating a new structure. So why is that not creativity, but transformative creativity is different? And we were trying to make this link. And, so Kenneth Stanley is talking about the unknown unknowns. So there are, like the Erdos thing, the unit distance problem. It's absolutely fascinating and exciting that there are all of these problems, and you can put them into an agentic harness, and it is intelligent, right? It can do this adaptivity, and it can solve problems, sometimes in weird and wonderful, wacky ways, but it solves problems. And now it can take that chain of thought adaptation, it can put it into its memory system, it can compress it, it can reuse it later. It's very exciting. We built intelligent systems, but why are they not creative? Because this is the other thing, that these LRMs and these harnesses came out, and I could see on its face that there was something, we call it slop, right? So when you use a bare LLM and I think of querying LLMs a bit like shining a flashlight into embedding space. Mm-hmm. So isn't it interesting that the more you are a domain expert, the more focused that flashlight is, the more of a perspective you ground the query in, the more coherent it is, the more creative it is, the more autonomous that you can make it. So we're trying to square this circle here. What is it about that thing? What is it about those harnesses that make the models more creative? And for us, it is simply the application of constraints. So you have a specification, you can run code, and the code can actually condition the output. You have a memory system, and within a perspective, you can make it creative. So a lot of this was just us trying to figure out what is intelligence, how is transformative creativity different.
I kind of wish I had more of a contrarian take on your thesis, but I totally agree with it. So maybe we'll have to create some devil's advocate questions here at some point. But couldn't agree more. And François is the co-founder of NDIA and creator of ARC AGI, the benchmark. So very, very aligned thinking there. But it's a pretty brave thing to jump in and try to define creativity in the realm of this sort of AI era. And it's not arguing about like, are they creating, results out of distribution, or are they only capable of remixing things, or, why is this jagged intelligence thing happening? You went right for the heart of like the most human piece of it, which, in a way we've kind of had to grapple with, because look, the first stuff for generative AI that was working was like image generation, which you would think would be like the last thing that it would be good at. I would have thought coding, maybe other language stuff, but like here comes Midjourney and these things. And it's like, oh my goodness, like right for the heart of creativity and humanity. What are you thinking, Jeremy?
What was very apparent when we were reading, the creativity literature in psychology and that sort of thing is, well, that literature was designed to study creativity in humans. And so there's a lot of these accounts of creativity that are very human specific and concerned with the things that humans are concerned with. And so what I think we were trying to do in the article was trying to come across a way of talking about creativity that was a bit more broad than that could sort of fit in with the way of talking about AI. And also, like, one of the impactful things was like this wonderful quote from Richard Feynman of like, someone asks him, can machines think? And he goes, well, a car doesn't go fast along the ground like a cheetah does, and a plane doesn't go through the air like a bird does. So a machine might not think like a human does, but could still be thinking in maybe some other sense. So then, trying to get at what is really important about that. And I mean, we do in the article kind of steer away from the art, this sort of AI art topic, because it's just it's an entire topic unto itself, and there's a lot going on in there. But so I think we were trying to focus a bit more on like creative reasoning and the creativity that's in science and that sort of stuff.
Even the art thing is interesting though, because we say in the article that being derivative that's what slop is. So being derivative is being like a photocopier. And a lot of AI art does look like it's a shallow mimicking, but art is interesting because the image is the prompt. And the image actually contains a lot of information. The reason why it's so hard to not make LLMs produce slop is you actually need to be an expert in order to frame the question in the right way to constrain it to not be slop. So the AI art thing is a bit of an interesting thing. But the thing is, though, like, I don't want it to sound like we're being cynical and saying that LLMs are stochastic parrots or anything like that, because actually we're not. LLMs, they acquire, and we can talk about how they acquire because it's quite interesting, but they actually have these abstractions, right? So, what we're talking about here is there are models of invariances and constraints that represent things about how the world works. And these models, they actually have, for just language, for example, they have syntactic competence. I was speaking with a linguist a couple of weeks ago. He was actually saying that they have better syntactic competence than humans do. They can skin sentences like an onion that humans cannot skin. And you ask them to explain how they skin that sentence, and they will give you a PhD level answer from linguistics textbooks. And now, I mean, this particular linguist, he had something quite interesting to say, which is that maybe they they took those abstractions from the linguistics textbooks. And, like I interviewed the 2 for AI guys, in Zurich the other week, and they showed me an episode on their ARC v3, the duck harness, and it was amazing. It said, this is a maze. we as a society, we've figured out all of these abstractions and we've put them into our collective zeitgeist. They're written about on Wikipedia, they're in books, and now you can use them as the basis for reasoning. Now we can kind of quibble about this, that are they the abstractions in the privileged sense that we know abstractions, right? Do language models understand syntax in the way that we do? Probably not. This is the whole thing that Kenneth Stanley was getting to with the fractured entangled representation hypothesis. So probably they're not as factorized, they're not as modular, they're not as abstract. Abstractions have privileged levels, right? There's a strong form of abstraction where you can actually do counterfactual reasoning. Right, so maybe these abstractions aren't as good as that, but we know for sure that you can take a context-free grammar, you can get it to productively generate language, and you can take a bare LLM, and it will learn statistical invariances, and it will recognize utterances produced from this. So there is some kind of abstraction happening, but the million-dollar question is, could language models, without these abstractions, if you just gave them primary text on the internet, would they be able to acquire these abstractions as part of the training process? Because right now, there's something magical about our abstractions, right? So we put them in the data, we create inductive priors and we train them on it, and that's how the language models acquire them. But could they do that tabula rasa? Could they do that de novo? That is the million-dollar question.
We have to ask the scaling question too. So much of this LLM world is about, okay, OpenAI, Anthropic, whoever, they double model size every year for a decade, right? Are we gonna get there? Are we gonna get to that creativity, or are we like just fundamentally optimizing the wrong thing? So it's a bit of answering the million-dollar question, Tim. What do you guys think?
Quick answer, only because I'm interviewing Tom McGrath from Goodfire tomorrow. And he's done loads of analysis on these neural networks, and he's looking for geometric structures and emergent factorization and so on. And he seems to be seeing empirically that as you train the models more, they do actually have more factorization. And it's not necessarily a statement about the type of computation they're doing or the type of thinking that they're doing, but there is more factorization. But there is an elephant in the room again, which is that we train the models for doing something quite simple. So, minimizing perplexity on next word prediction. So it's kind of weird that they would learn these abstractions anyway. But so, when folks said scale is all you need, they were wrong. Right, the systems we have now, they are neurosymbolic systems. They're agentic harnesses. They're co-trained with us. We place constraints in. We're in a very, very different world now.
Yes.
And in the future, we might be in another different world, right? Because we might train these systems with intentional feedback. This is what Tom McGrath is talking about, basically. So, imagine if we actually had some supervisor model during training that was encouraging this abstraction, this kind of emergent factorization. And then we do this whole harness engineering thing on the side. So the kind of AI that we're going to have in a few years' time will be unrecognizable.
Just to add a bit more sort of theory onto this of what Tim was talking about earlier of this syntactic competence. But what we sort of really want from AI systems is more the sort of semantic thing of when we talk about understanding in the context of an LLM, then that it needs to know what the words mean that it's manipulating and not just manipulate them as sequences of tokens. And there are many philosophical accounts of where semantics comes from. I'm not going to say which one is right, but the one I like the most is sort of thinks about semantics in terms of the selectional history of the components of our bodies, for example. It was important in our evolutionary history for us to be able to accurately represent what was going on in the external world. Therefore, we developed organs whose purpose is to represent what is going on in the external world. And that's how sort of the thoughts that are going on inside my brain bear some resemblance to things that are going on far away from me. So we can then talk about what's going on in the training of a large language model, because then that's its selectional history. What abilities was it selected to have? And the Stanley Picbreeder experiment is such a fascinating example of where you can have the same neural network architecture, but trained using very, very different means. And when you do it in one way, you get these fascinating, deeply semantic seeming representations. It can, open and close the skull's mouth. It can turn the butterfly into a fly, or all of these cool things that it can do. Whilst when they did it in the just purely, brute force SGD, you got this complete spaghetti. But actually, the Picbreeder experiment is a little bit limited. That, when we generate images with AI in reality, we use things like, diffusion models or something like that. And we do know that diffusion models learn interesting representations. There's this wonderful paper that talks about how they learn what are called, I think it's geometry adaptive harmonic representations. And part of what's going on there is that because the small diffusion model has to learn how to denoise a wide, massive variety of images, it has to start learning some form of general features in order to successfully perform that denoising over this broad range. So there is something that happens when you make the training data bigger and the models bigger. And actually, there's been been a bunch of theory on exactly how much data and model size and whatnot that diffusion models need. So there is things that go on there, but I think that's the important thing going forward is going to be ways of thinking about training so that the important abilities that we want from these systems, their abilities to have world models and break things down into their constituent parts and recombine things and all of that is going to have to come out of what was selected for by the selectional process that gives rise to these systems.
I mean, it might be worth just very quickly mentioning that folks should look at the Picbreeder experiment from Kenneth Stanley. But it produced these beautiful phylogenies that had this factorization. So things like symmetry would be locked in, very low down the phylogeny. But it was an interactive form of learning. So essentially it was using these pattern, these compositional pattern producing networks, these CPPNs, and humans would breed interesting ones together. And as François Chollet says, the human, the feature of human cognition that's fascinating is we can look at an image or some text and we can decompose it into its abstract constituents. And that's what humans did when they were choosing those images to breed together. And actually, very interestingly, about 2 days ago, Sakana in Japan, they recreated the experiment in a non-interactive way. So they actually got visual language models to select which images they thought were interesting, and they created this phylogeny. They evolved it. And what they found is that it didn't quite produce the same kind of factorization as the humans did. And that is presumably because the language models don't quite have that ability that we have, so they can't spot the abstractions. But if there is even an opportunity or a gradient towards factorization, if we could scale up these methods to create networks that do have more modularity, more factorization, that would be fascinating because there are hints of it. Like I'm sure many folks at home would have experienced this, that you can write an essay and the language model is a brilliant critic, right? You can say, have I spelt this right? Or can you give me a critical appraisal of it? And it's wonderful. It's really good, but it can't generate it. So why is there a generation discrimination asymmetry? Why is it so bad at producing or generating, but it's so good at discriminating? Like this is a really interesting thing, and this is kind of where our intuition led us to this article.
Jeremy, you said understanding there. I think it's worth spending some time kind of understanding. So one big claim of the paper is understanding, not prediction, is what enables creativity. So do you sort of both equate understanding with respecting constraints? Why would that be the right definition?
I think the key thing to say here is that like the constraints are what is understood. So in more general, like we talk about how you need to understand the phylogeny, the sort of the history that produced the ideas and tools and objects that you're considering in your domain. And then like, what is understanding? So understanding is one of those words in philosophy, and therefore there are 100 different theories of what exactly it means. But sort of broadly speaking, like understanding is to do with grasping how things hang together in a sort of network of things. So, for example, like if you just want to have a really accurate knowledge of what the Earth's climate might be like in the next few years, then what climate scientists do is they build these incredibly big, complex computer models that incorporate every single factor they can think of and can model. And so that's great for like producing accurate knowledge. But if you want to understand the Earth's climate system, then what you often want to do is build a smaller model by throwing things away and trying to see what are the important things that we need to keep if we want to describe the behavior in any way that's sort of reasonably accurate. And so understanding is really about this sort of ability to ask what-if questions. And by doing that, that sort of helps unlock creativity, because sort of you now have a feeling for what all the different levers you can pull are in some space and what happens if you pull them. And then, like understanding isn't a binary. It's not just like an on-off thing. Like we talk about these different levels of understanding. So like you've got an incredibly shallow understanding where you just understand like an image as a set of pixels, or like a painting as a bunch of oil on canvas. And so like a forger can understand like the Mona Lisa at the level of oil on canvas and then make another one. But if you ask them to paint a new portrait of the same quality, they're not going to be able to. And then you get like the domain-specific understanding of like understanding things within their environment and starting to build a bit more of a deeper feeling for what matters. And then finally you get like to sort of the domain general understanding, where like by understanding your tools in themselves, you can then sort of, you can think outside of the box, because you can understand what happens when you take your tools out of the box and try and create in a different domain.
I know, and I love to use this term abstraction mountain. It's a wonderful metaphor. And it simply means that the further you go up the abstraction mountain, the more you're screening off detail, the more domain general it is. Just as we were saying about on MLST, we try and communicate high up the abstraction mountain. But if you think about it, though, it rather licenses this idea that there are multiple ways to understand things, right? And also, we are quite anthropocentric in how we talk about this, because we privilege really, really high abstractions. And mathematicians, when they were writing proofs for hundreds of years, so many things went without saying, because they were just describing things in abstract terms, and we can use this strategy. I don't need to explain that because we've done it before. And now we have, like these GPT models, they're disproving Erdos, theorems, right? And conjectures, and hundreds of pages of description. And the thing is, now we're in an interesting situation, because this is a very low-level, verbose, concrete understanding, and we don't like that as humans because it's illegible to us, right? But in a weird way, even though there are constraints in that process, are there actually more degrees of freedom? Can we actually do more if we admit, larger spaces to operate in? Is it a given that having really, really high abstractions up the mountain is what we want with artificial intelligence? It's a good question.
And this is a point on which like Tim and I have disagreed in terms of, I think Tim, you like to think of sort of deep understanding as being very abstract and sort of, but I think there is also a difference in, you can gain in understanding that actually takes you from sort of abstract to more concrete. So this is something that came out in sort of the history of chess, that, when you learn chess, you sort of start off by playing random moves, and then you might sort of start learning some rules, and these rules sort of tell you, develop your knights before your bishops, and move, don't move pawns too many times in the opening, and these sorts of things. And for a while, it was sort of thought that like really good chess play, obviously the top chess players recognized that there were exceptions to these sorts of rules, but the idea was, we can just try and create a better set of rules and a deeper, more abstract way of thinking about it. But actually, what has really emerged in chess understanding, maybe since sort of like the 1990s or so, is that a lot of deep understanding in chess is about concrete understanding of being able to sort of situate yourself in a particular position and understand what the principle inherent in the position is. And some of that was even going on in the 1920s, but it sort of came more and more to the fore in recent years. And that more sort of concrete way of thinking about chess is partly what like Stockfish or AlphaZero or whatnot are doing. They're exploring within the game tree and trying to find the important lines in the game tree, but they're still not at the level of sort of depth of understanding. They're stronger, they're more intelligent in a certain sense, but they're not thinking about, well, what if this pawn wasn't on the board? Then what could I do? What would be the lines there? They don't have that counterfactual thing going on. Yeah. But I think there is this depth of concrete understanding that, like, you know, an amazing sports player, they just have this inbuilt sensibility for what their body can do. And if they're, you know, a tennis player or something, they'll know how the ball is going to bounce, and they'll be able to use that understanding to very quickly adapt if, say, the design of tennis balls changes, which it has over the years, or these sorts of things. Whilst if you had a sort of rigid rules-based thing, you wouldn't be so able to do it. But yeah.
I mean, just to very quickly comment on that. I mean, I actually agree with you that in some sense, the concrete understanding is more privileged. As an example, when I read François Chollet's Measure of Intelligence paper, or when you go to university and you learn about mathematics, you're kind of told the information in a very rigorous way. So this is the result of evolution. So many mathematicians for decades, they've distilled, and that is actually the worst way. I mean, it's still actionable. You can take that abstract knowledge and you can do things with it, but it's only after years of reflection that you actually build up. So you have this kind of concrete, grounded understanding, and you build up and you meet those abstractions up the mountain. And that's when you have that visceral feeling in your gut. You're like, I understand it now. And that actually enables more creativity. The reason why we were able to kind of, flit between François' ideas and Kenneth Stanley's ideas is because we kind of worked up. So we met them where they were. So, and this is the same thing about, we talk about symbolic AI and is the brain symbolic? I have a theory that the whole symbolic thing is almost a crystallization. It's a skill. It's the output. So does our brain actually think symbolically, or is the symbolic program the crystallized skill that we use to communicate with other people, and it's like a mimetic thing? Yeah, I mean, it's a fascinating question.
Tim, you're just full of fascinating questions. We could just run you on like an agent loop, just asking yourself questions, and then you could do the whole podcast. Wait, I want to ask you both something. So, humans learn statistically from experience. Like, why is interpolation like acceptable for humans, but like not sufficient to sort of, enable creativity for machines?
I mean, what I would say is that humans, I mean, sometimes we do interpolation, but we're doing more than that. So, we distill what we've learned from experience and try and generalize it. And, we're doing a lot more than just like taking the ideas that we've had from experience and then just sort of smashing them together to make more. So like, to give a really clear example, I guess, of what I mean by like interpolation of, if I take, an image model, and let's say like maybe an older one, like a GAN or something, I just give it a bunch of ordinary face images off of some database, then it will be able to sort of traverse the manifold of those face images, and it'll be able to make faces that didn't exist before. And there's thispersondoesnotexist.com is like a website that will happily do that for you. But what it will never do is, if none of the images in the training data had like a person with an eye patch, it will never make a face image of a person with an eye patch. It's not able to sort of iterate on these things and say, well, what if they were different in some way I've never seen before? And that's something that we can do as human beings. And then we can go even further than that, like, definitely what this system will never produce is like a, Picasso painting that entirely reinterprets what a face could look like to express some different perspective on grief or whatever it is that he's trying to portray. And so like, we're never quite satisfied with just thinking about the way that things are, and we try and have this curiosity for how things could be different in all these sorts of different axes and whatnot. And
yeah, absolutely. That's a great answer, by the way. Thank you, Jeremy. I mentioned this kind of lovely writing in the paper earlier. There's a thing in the postscript. I think it was, you said, the history of symbolic AI is a cautionary tale about assuming the world decomposes that neatly. Tim, where has symbolic AI, like, why did it stall out kind of, in earlier, generations of symbolic methods in the past? And do you see an opportunity for combining deep learning and, symbolic methods to go further down this path of intelligence?
I do. I mean, you're touching on a very interesting tension there. And as I said earlier, I was very inspired by Marvitsa Chiramuta and also folks like David Krakow at the Santa Fe Institute. And so, I mean, François is my hero. But he has a very strongly held belief, which is that the world is decomposable into these abstract structures, and I think a lot of that is true, right? Because when we talk about these constraints and invariances, what we are saying is that there are pockets of the universe that are compressible in this way. And these symbolic representations are incredibly powerful. They're more powerful in many ways than the neural network representations, simply because you can represent an infinite space with a finite number of symbols. It's very, very interesting. But when we speak to folks, doing complexity science, they actually say that it's not quite that simple. That there are phenomena in the universe that are not reducible in that way. I think this symbolic idea is an extremely good way to do many types of cognition, but I think we also need something else.
Jeremy, do you have any thoughts on the symbolic side?
Yeah, I broadly agree. And I think the exciting thing in, going forward in deep learning is sort of trying to, come up with these various sort of hybrid things, taking sort of the symbolic structures, that we have and combining them with the power of the ability of these deep learning systems to adapt to very particular patterns. I think that can be the problem with a sort of very rigid symbolic way of thinking of it. It's sort of you're trying to treat everything in this by some very general rules. You're sort of trying to find the rules that describe everything in the universe. And maybe those rules exist, but one of the things that I also find to be interesting is this idea of sort of particularism of individual situations have their own logic to them. And can you discover that particular logic? And I think maybe that's where sort of neurosymbolic can try and do both things at once. Or one of the analogies we use in the paper is this beautiful video that the YouTuber 2Swap made about Klotsky, which is this game of moving blocks around. But when you sort of map out the possibility space of that game, you sort of get these blobs of particular types of positions, and then they're linked by these narrow edges that bring you into different blobs. And these different blobs have different numbers of degrees of freedom. They essentially follow their own individual logic. And so creativity is the exploratory creativity that Margaret Bowden talks about is sort of when you're within a blob and trying to understand the rules, the logic that sort of allows you to make new things within this blob. And then sort of transformative creativity is when you go out on one of these narrow paths and find somewhere else and then have to figure out how to explore that new one that could have completely different rules. And, there might be rules that govern the whole thing. I mean, in Klotsky there are. It's still just moving blocks around. But those rules might be too difficult for us to ever work with. If you want to understand what happens when you put milk into your tea, you don't start by solving the Schrödinger equation.
Right.
I mean, I think it's a tantalizing idea, though. We've spoken to so many scientists who are universalists, folks like Stephen Wolfram or Noam Chomsky with his original transformative generative grammars, Carl Friston and so on. And, it's a tantalizing idea that we can take a very complicated universe and we can reduce it down to some simple rules. But I'm a fan of emergent specialized intelligence, right? I think that we need to wrestle with the fact that we are computationally limited, right? I'm even using the word computationally, but basically our brains are limited. And that's why what we do is we adapt to situations. And, there's this kind of continuum, right? So we start with high adaptivity, and then we move into a domain, whether we're doing agentic engineering or whatever it is, and we specialize through optimization and building crystallized skills. And that's just kind of how the world is, right? So we're optimizing in all of these different domains, and we're building these crystallized skills. And yeah, it would be wonderful if we could have the one true skill, the one rule that does everything in the universe. But I don't think that's even necessarily something we should be aspiring to do. What we should be really trying to do is just building these adaptive processes that meet the need and specialize in these various different situations. Because knowledge and intelligence, in my opinion, is quite perspectival. It is quite situational.
I know, the sort of conclusion this paper draws does not feel very like anti-LLM to me. I mean, you kind of called that out earlier, Tim.
Not so.
And I know you happen to be one of the most agent-pilled people I know in terms of how you use it in your workflows and production of your podcasts and this kind of thing. Jeremy, I still have yet to learn about how you're using AI in your workflows. But I mean, it's inevitable that we're going to compare, as we're looking at intelligence in this example that we have, the existence proof of the human brain and how we exhibit creativity. We're going to compare like that. But what do you think is the future of, where AI goes in terms of, being more like human intelligence, more sort of AGI-like, or are we going to do what you're saying, Tim, and we'll have this specialized AI that will be tools for humans? Is it going to be a collaboration? Like, paint a bit of, the way you see the future going, maybe, midterm, not necessarily like, who knows what the heck's going to happen in like 50 years, but, 20 years-ish.
Yeah, I mean, I think we're already seeing something very exciting happening, which is that, what we have now are not LLMs. It's incredibly sophisticated. So yeah, we have these big foundation models, and they do this LRM, so this chain of thought adaptation. We have these agentic harnesses, and something very interesting is happening because not many people actually have seen this yet. I'm starting to see it. I thought that LLMs would always produce slop. And now when I do my agentic triage, it has basically learned a simulacrum of Tim. And that is because over the course of months, every time it sends an email in the wrong way, I've got a process every day that corrects it, right? So it knows how to sign off. It knows what Tim would say in this situation. It knows how Tim deals with customers. It knows how Tim does it, And this is basically a snapshot of the whole thing because LLMs are, it's not LLMs. The systems are becoming more adaptive. And have you noticed even the prose and the language they use, it's kind of annoying now because it's far more like us. I know the word load bearing is very annoying, but I've started using it because I actually like it. Right? And what's happening is, like, even when we build these memory systems, yeah, they're spaghetti. And when I move information into Notion, it's spaghetti, but I'm always training it not to be. I'm always saying, don't repeat yourself, don't append, replace what's already there, compress it, represent it like this. And every time those trajectories go back to Anthropic, the models are getting better. They're becoming more and more aligned with us. And the models are also becoming more reward-seeking with all of this RL training. So they're becoming far more autonomous. And they're working with much higher level abstractions because we're constantly training them. So I actually think we live in very, very strange times because the world we live in now is kind of converging towards something. And that something, I believe, is more of this kind of emergent, specialized intelligence type story rather than the monomaniacal, super intelligent AGI thing that we were talking about before. And I think that's honestly a good thing because there's still so much opportunity for expertise. These things are only really as good as your ability to understand a domain, to frame the question in the right way. I mean, the way I do agentic engineering is quite interesting, actually. So, I build an app and it's a little bit like the phylogeny. The DNA is the code. So, I understand the domain and I put the schemas in there. I put the database structure in there. These are the core constraints. And now there's this new ontogenic adaptation, which is that every time I use the application, I'm crystallizing the skill. I'm saying, next time, don't do that. That was a silly thing. Update yourself. So there's this kind of like ontogenic adaptation and memorization. And then there's this cultural learning thing on the top. So it's now, reading things from Wikipedia. It's posting things on Twitter. And you see, you have these 3 levels of knowledge accumulation. And we as humans, we are very much in the loop of adapting it, specializing, helping it learn. So yeah, it's a very exciting time. And we're seeing this play out now.
one thing that I was thinking about from what you said I think we don't want these LLM, our AI systems to be, all too human-like in that, well, like, there are plenty of humans. We know, we know what it is, we have plenty of human intelligences. We can, if we want to talk to human beings and that sort of thing, then that's something we've always been able to do. I think the thing that, we conclude the article with and sort of conclude the article with is this idea of like human AI co-creativity, that like the thing that I'm excited for in the future is what, these systems can do together. And if we're, if we want human AI hybrids to be, as interesting as they can be, then kind of we want AI systems that are quite different to humans. And I mean, there is one rather important like aspect of human creativity that maybe isn't particularly represented in AI systems and won't be unless we sort of rather radically change a lot of things about AI, is the sense that like a lot of human creativity is about having an experience of the world and building, a perspective on what it is like to have had that experience, and then trying to share with other people so that they can see sort of what it is like to experience the world in that way. And like AIs don't experience the world. They're not conscious and these sorts of things. Maybe Anthropic is starting to talk about that sort of stuff, but I don't think we're there yet. And that I think is particularly important, like when it comes to domains like art, where so much of art is about that sort of expression. And so that's going to be a part that is heavily about human beings, and it's a whole sort of tangled web of ethical things about the development of these systems and the ways that they produce art. And I think we don't want to get tangled too much in that, because it's not really what the article's about. But yeah, but when we sort of think about the creativity in more like the scientific domains and that sort of thing, then we're already seeing sort of some of the power of having these systems as like an engine to help us answer new questions. And like, chess was completely transformed by the development of computers that could play chess. That not only did these computers play chess at a level that had never been seen before, they encouraged people to be more creative in the way that they played chess. That there were all sorts of sort of dogmatic ideas about strategies and openings and this sort of thing. And the computers just blew half of those out of the water and said, no, you can play that opening, it works. You can do all these sorts of different things, they all work. And so I think that is one of the great things that, like, when a system that does things completely differently to how humans does things, it can expose to us a lot of our biases or the ways that we've been doing stuff. And we sometimes flatter ourselves that we are more creative than maybe we are. I think a lot, this was the thing that Lee Sedol said about Go after AlphaGo beat him. That what AlphaGo had shown him that a lot of Go play, a lot of strategies in Go that people thought were creative were actually conventional. I think this is also going to be true of a lot of science, that there is a lot of science which is about turning the handle of, we have this hypothesis, we know how to build the experiment, we need to still build the experiment and analyze the results. And so I think, these systems can already help us accelerate that. You're asking how I've been using AI in my workflow doing mathematics. And, I haven't been doing any of the grand sorts of stuff that like OpenAI has been, of like trying to build agentic harnesses to, solve questions in this autonomous way. But what I have been using it for is, there's just a lot of drudgery sometimes of, a long calculation that's going to take me a few pages, and being able to do that and automate that in a way that's a lot more flexible than like Mathematica or anything like that ever was. So I think that, there is a lot to be gained from these systems that do things in a complementary way to humans.
Yeah, I feel like one call to action there is if you have free credits for AI to throw at Jeremy, please do it. Let's see what he can do with even more compute. Well, just wrapping up, you both have such a cool perspective on things. I think we've built up quite the sort of worldview throughout this exploration and this conversation and in this paper. Where do you see, something very exciting for, it's mostly, AI researchers watching the show. Where are some interesting areas to dig, for cool ideas? Like, Tim, let's start with you. You've looked at all kinds of stuff, like even, how the brain itself functions and getting into more biology and, who knows what else you'll get up to. I can't wait to see future documentaries. But what do you think would be an exciting kind of, thesis for folks choosing what to study in, maybe a PhD program?
Well, I'm clearly biased. So, there are many tribes in the AI space, and we've tried to cover all of them. There are the Bayesians, the neural network folks, the biology folks. So I'm an evolutionary guy. So I try to be hybrid and take ideas from different places. So I think there's something very, very special about evolution. And it's quite interesting, isn't it? Because I think we talk about the ARC challenge all the time, and as I was saying to the TUFA guys the other week, it's absolutely amazing that on version 3 of the ARC challenge that it can actually acquire a goal. Right. And it can use abstractions from its training data and it can reason around them. But the one thing that seems to be missing is, first of all, compressing that adaptation and reusing it. So library learning and transfer. But also, this synthesis, this creation of abstractions in the first place without bootstrapping. And I have a deeply held belief that the reason why we have acquired these abstractions, they've been kind of gifted to us by the laws of nature. And, many folks say, it's because of, nativism, for example. For some reason, we have these programs in our mind that do these things. I think it's because we've been on this process of evolution. It's because that we co-evolved with the world and these very low-level abstractions got locked in early on. And for me, being able to recreate this in an algorithm, so it might be something like an artificial life type algorithm, and being able to scale that the way that we have scaled large language models, I think that could be very exciting.
Woo! All right, that's a cool call to action. I love that. Jeremy, how about you?
Yeah, so I have a couple of thoughts. Of one of them sort of coming particularly biased from mathematics, of like, I think there are a lot of mathematical frameworks that can be explored for application to AI problems, and ways that we can try and sort of combine that stuff that we figured out and that we have a deep understanding of why it works, and add AI systems into the mix for that. So some of that is like, interested in thinking about, the infinite limits of neural networks. A neural network has a finite width and a finite depth, but we can represent mathematically what it would look like if it had an infinite width or an infinite depth. And then you can actually go back to the finite at a different point. And this gives rise to cool there's architectures like neural operators that sort of take this idea of sort of going into the infinite and back again. And I think that's one of the really cool things that the mathematics lets you do. And then, I gave a talk to some of the ARC Prize community Discord on one of the areas that I'm interested in is something called inverse problems. And you can think about ARC as an inverse problem. And then all of these different methods that mathematicians have come up with for applying to inverse problems give different perspectives on ways to go about thinking about ARC. And so that's sort of one side of things. And then a different side is, I've been thinking about benchmarks and how, like, benchmarks are these static measures, broadly speaking. Like even something like ARC 3, you play the game and then it tells you that you've succeeded or not succeeded. And one of the things that we touch on in the paper is this sort of persuasion is a really important aspect of creativity, of creating something new and then being able to persuade others who weren't looking for it that it's actually what they wanted. And you can't persuade a benchmark. It either gives you a score or not a score. And so, like, thinking about different ways that we can test these models, and maybe drawing a bit more from, like, maybe from animal psychology and the way that you try and think about, the cognitive capabilities of a bird or a snake or something, or thinking about things from, we don't do, we don't do very many randomized controlled trials and that sort of thing in the AI space. And, we know that those are really good for testing how medicines work and that sort of thing. So I think there's a lot of like experimental frameworks that people have been developing for a long time that maybe we could try and incorporate into the AI space to have a better idea as to like what's going on.
Yeah, just a quick thing on that. I mean, Jeremy said before we started recording that, isn't it interesting to think, could a solution on Arc v3, could it be transformatively creative? And you were saying that it could be, but the benchmark wouldn't tell you.
Yeah. I mean, there were so many communities in video games of like unintended play, of playing the game in a way that does not care one bit for the, stated objectives of the game. And, if someone decided to do that with the Arc 3 games, they might be able to do all sorts of cool creative stuff, but like the verifier will go, what the hell are you doing? Like, I don't understand you. And yeah, so I feel like that, I don't know how we could do that very easily. I mean, there are some benchmarks out there that aren't really benchmarks. They like have human judges. And so they exist for like one paper, but then no one can, no one can test their things against their, and those can be a little bit more flexible with what they allow because, you can get an unexpected solution and go, oh, well, actually, no, I like that. But yeah, how, the standard pipeline of just like model comes out, it has a bunch of numbers that say that have, that hopefully are higher than the other people's numbers, that there are too many limits to that. And yeah,
all I'll say, I won't say much, but Arc AGI 5 is already begun development. So that's all I'll say there.
Okay, nice.
Oh, interesting.
Stay tuned.
I'm very excited to know.
But I really appreciate you both.
I've heard a couple of rumors, but I don't know if it's...
I mean, it's early. We're actively building 4, and then, 5 has, design specs and things like that are stewing. So, but yeah, I won't share any more. There'll be plenty to come on that. You'll be first to know, Tim. Don't worry.
Oh, yes, absolutely.
I appreciate you both. This paper was more wide-ranging and just, rich, I think, in terms of sources and topics than many I typically cover on the podcast. So thank you out there for everyone watching, thinking of this as a paper to cover. And just also thank you both for all your contributions to the ARC community. Over the years, specifically Tim, I can't thank you enough for just how invaluable your contributions have been and sort of rallying the community and inspiring people to check out this, what was once a less known benchmark, but now seems to be more widely known, but still has a lot of work to do. And so, it's greatly appreciated and very impressive, the work that you've done. So thank you. Thank you both for joining me.
I appreciate you guys. I mean, Arc was really the only adaptation bottleneck. I mean, thank God that Chollet, isn't it amazing that Chollet understood this so early? Right. And like all those years ago, he was talking about the need to actually have adaptive synthesis of skill and a benchmark to measure that. He was so early. So, it's down to Chollet, really.
Yeah, no, thank you for all you said about the paper. I'm really glad that you liked it.
I loved it.
It was fun to write.
I loved it. Please write more. We're here for it. More MLST papers, but I know it's a lot of work, so no pressure. Well, I appreciate you both, and hopefully you all listening out there see that if you suggest amazing guests, I will go get them. So I want to hear from you all. Comment in YouTube. Make sure to subscribe, all that good stuff. And I look forward to seeing you next time on Abstract Synthesis.